Next, we move on to scalar multiplication. So what do we essentially mean by scalar multiplication? Essentially, as I had mentioned before, scalar multiplication can be used in this sense as well. So we can use scalar multiplication to alternatively define subtraction as a step forward from addition. So we have a particular scalar element, and here in this case, we refer to scalar element as one particular element. So when we talk about matrix A, we have a set of numbers, right? There is a particular representation of different numbers in a particular form. We have 4 numbers over here, we have 4 numbers over here, and we have mentioned before that there can be more than 4 numbers in that particular matrix as well. So when we talk about matrix, it's essentially a cluster or an array of data. But a scalar number is a single number. It's let's say scalar is, let's say it's 2. So, but A is not a particular number. A is a matrix, which is an array or a group or a cluster of numbers. So that's something that needs to be noted when we talk about scalar multiplication. Essentially, it's the multiplication between a matrix, that is a cluster of elements, and a particular single element. What we do is this scalar element gets multiplied with each corresponding element of the matrix under consideration. So here, if you have noted, the condition that matrices needs to be of the same dimension need not be there, because in case of addition and subtraction, the operation was between 2 matrices. The addition subtraction operation was being conducted under 2 matrices. But in scalar multiplication, we are talking about only one matrix. The other is actually a number. So here that condition need not hold. You can talk about scalar multiplication for any dimension of matrices. It does not matter. Now, how do we define it? So lambda A, if matrix A is represented by the elements Aij, let's suppose A has the dimension m cross n, then again lambda n will also have dimension m cross n. So the original dimension gets translated into the product, and every element of Aij gets multiplied with lambda. So take an example, let's say lambda is 2, and I already have A as my matrix before. So let's say this is A, 23, 46, 290. So what I do is I multiply 2 with 23, that's the first element. I multiply 2 with 46, that's this element. I multiply 2 with 2, this element gets multiplied with 2 as well. So I have 2 into 2 into 2. And finally, the A22 element also gets multiplied with 2. Note that all these elements get multiplied by the same number. So lambda is a common factor which gets multiplied with all these elements. So this 2 gets multiplied with all the particular elements of the matrix. So we have 2 times 23, 2 times 46, 2 times 2, 2 times 90. Compared here, 2 times 23, 2 times 46, 2 times 2, and 2 times 90. So the result is simple. 2 times 23 is 46, 2 times 46 is 92, 2 times 2 is 4, and 2 times 90 is 180.